All right, welcome to Module 3.3. We're going to be getting into what happens when atoms become unstable, and we're going to look at radioactivity. But to get us started, we're actually going to jump straight into a video looking about the history of radioactivity, and in particular at Marie Curie. So I'm going to play that for us now.
If you want a glimpse of Marie Curie's manuscripts, you'll have to sign a waiver and put on protective gear to shield yourself from radiation contamination. Madame Curie's remains, too, were interred in a lead-lined coffin, keeping the radiation that was the heart of her research, and likely the cause of her death, well contained. Growing up in Warsaw, in Russian-occupied Poland, the young Marie, originally named Maria Skłodowska, was a brilliant student, but she faced some challenging barriers. As a woman, she was barred from pursuing higher education, so, in an act of defiance, Marie enrolled in the Floating University, a secret institution that provided clandestine education to Polish youth. By saving money and working as a governess and tutor, she eventually was able to move to Paris to study at the reputed Sorbonne. There, Marie earned both a physics and mathematics degree, surviving largely on bread and tea and sometimes fainting from near starvation. In Paris, Marie met the physicist Pierre Curie, who shared his lab and his heart with her. But she longed to be back in Poland. Upon her return to Warsaw, though, she found that securing an academic position as a woman remained a challenge. All was not lost. Back in Paris, the lovelorn Pierre was waiting, and the pair quickly married and became a formidable scientific team. Another physicist's work sparked Marie Curie's interest. In 1896, Henri Becquerel discovered that uranium spontaneously emitted a mysterious X-ray-like radiation that could interact with photographic film. Curie soon found that the element thorium emitted similar radiation. Most importantly, the strength of the radiation depended solely on the element's quantity and was not affected by physical or chemical changes. This led her to conclude that radiation was coming from something fundamental within the atoms of each element. The idea was radical and helped to disprove the long-standing model of atoms as indivisible objects. Next, by focusing on a super radioactive ore called pitchblende, the Curies realized that uranium alone couldn't be creating all the radiation. So, were there other radioactive elements that might be responsible? In 1898, they reported two new elements: polonium, named for Marie's native Poland, and radium, the Latin word for ray. They also coined the term radioactivity along the way. By 1902, the Curies had extracted 1/10 of a gram of pure radium chloride salt from several tons of pitchblende, an incredible feat at the time. Later that year, Pierre Curie and Henri Becquerel were nominated for the Nobel Prize in Physics, but Marie was overlooked. Pierre took a stand in support of his wife's well-earned recognition. And so both of the Curies and Becquerel shared the 1903 Nobel Prize, making Marie Curie the first female Nobel laureate. Well-funded and well-respected, the Curies were on a roll. But tragedy struck in 1906 when Pierre was crushed by a horse-drawn cart as he crossed a busy intersection. Marie, devastated, immersed herself in her research and took over Pierre's teaching position at the Sorbonne, becoming the school's first female professor. Her solo work was fruitful. In 1911, she won yet another Nobel, this time in chemistry for her earlier discovery of radium and polonium, and her extraction and analysis of pure radium and its compounds. This made her the first, and to this date only, person to win Nobel Prizes in two different sciences. Professor Curie put her discoveries to work, changing the landscape of medical research and treatments. She opened mobile radiology units during World War I and investigated radiation's effects on tumors. However, these benefits to humanity may have come at a high personal cost. Curie died in 1934 of a bone marrow disease, which many today think was caused by her radiation exposure. Marie Curie's revolutionary research laid the groundwork for our understanding of physics and chemistry, blazing trails in oncology, technology, medicine, and nuclear physics, to name a few. For good or ill, her discoveries in radiation launched a new era, unearthing some of science's greatest secrets.
Alrighty, so as you can see there, Marie Curie was a fascinating woman. A bit of a summary there. She was born in 1867. She lived in France with her husband Pierre Curie, and he was a really big supporter of her, which is really great to see. And in 1898, she and he discovered polonium and radium. She actually won 2 Nobel Prizes. The first one she shared with her husband and someone else called Henri Becquerel, and that was in 1903. And then she won one herself in chemistry in 1911. So she actually had 2 Nobel Prizes, one as you can see there in physics and the other one in chemistry, which is very awesome. So let's get into a little bit more about atoms and what happens when they become unstable. Now, protons and neutrons, we already know they live in the nucleus, but what we haven't talked about is why they stay there, and that's because they're held together by what's called the strong force. Now, the strong force is just this strong force that holds protons and neutrons together. It's one of those terms where you can see scientists have been really imaginative with the name. But basically, your nucleus is normally stable, but it can become unstable, where that force is no longer really strong between them. And this basically happens because the overall size of the nucleus has either too many or too few neutrons. Basically, the ratio of protons to neutrons just becomes such that the nucleus is no longer stable. So some isotopes of an element are stable, while others are unstable. When they're unstable, they're radioactive, and so we call them radioisotopes. All right, so you can see over here with carbon, carbon 12, carbon 13, both totally happy, both perfectly stable, with their different numbers of neutrons in their nucleus. But as soon as we get up to carbon 14, where we have 8 neutrons, that ratio of 6 to 8 protons to neutrons in carbon 14 means that it's no longer happy and it's unstable. So that's a bit sad there. So what do atoms do? Well, they want to become stable. So to do that, they're going to go through what's called radioactive decay, or sometimes called nuclear decay as well. Basically, that nucleus is no longer stable and it's going to break down until it is stable. And that means it's going to also get rid of things in doing so. So we start off here with an excited nucleus. And that's going to decay. You're going to end up with a stable nucleus, some energy, and possibly particles, or particles instead. And that's your radiation. That's what we're going to be talking about today. So what is radioactivity? Well, radioactivity is just the emission of energy, and that's getting emitted either as particles or as electromagnetic waves. And it's caused by the spontaneous breakdown of the atom's nucleus. So it just happens. That's what we mean by spontaneous. Really, the only thing there, the only cause behind it is because it's not stable because of that ratio of protons to neutrons. But we can't predict when it's going to break down. It just will do it at some point. And in doing that, it's either going to get rid of particles or some electromagnetic radiation, and it's energy, and that's how it's going to get rid of that, and it's going to become stable by doing that. Now, these reactions are called nuclear reactions, and a lot of energy always comes off when this happens. Okay, they're spontaneous, like I said. We know sort of what generally is the cause, but we can't predict necessarily when that's going to happen. And there's no effect that we can see with temperature, pressure, or using catalysts. We can't speed these reactions up, we can't slow them down, we can't turn them off either. So they're very different from other sorts of reactions when we talk about like chemical reactions and that sort of thing. So a couple of things to be aware of: the difference between nuclear fusion and nuclear fission. So nuclear fusion is where things fuse or join together. So this is where you take nuclei from different atoms and you join them together to create one big nucleus, and this will also release energy. It happens on the sun, and you can hopefully know that the sun emits a lot of energy. It's producing a lot of energy. It's very, very hot. And so this is what's actually heating the sun and giving us all that wonderful sunlight, is nuclear fusion. On the other hand, if you have a nucleus and you split it apart, this is what we call nuclear fission. So this is when a large nucleus actually splits into several smaller nuclei, and when it does that, it also releases energy. Now, this can be spontaneous, and this is what we're talking about often when we're talking about like radioactive decay. So like I said, it can be spontaneous, and generally this is what's happening in nature. We have realized that we can trigger it, and we can trigger it by bombarding the nucleus with neutrons. So if we fire neutrons at that nucleus, we can basically just push it over the tipping point, and we can cause it to actually split and release that energy, which is handy when you're doing this in a nuclear power plant, because that's really what we're trying to do there, but also pretty devastating if it's part of an atomic bomb that you're dropping on a country, which is basically what happened in World War II. So that is the two different types of nuclear reactions you can have. Nuclear fusion, where you're combining things, or nuclear fission, where you're splitting the nucleus. So this results in three types of radiation that we're interested in, okay? And they're named after the first three letters of the Greek alphabet. So we have alpha, beta, and gamma. Now, alpha and beta, you can see there, they're both particles. So you have alpha particles and beta particles. This means they're a physical thing. On the other hand, gamma is gamma rays. It's just electromagnetic radiation. It's like light. Okay, like colored light, sunlight, like microwaves, radio waves, that's the same idea. It just happens that gamma rays are really energetic. There's a lot of energy in them, which means they can actually cause a lot of damage. Now, the type of decay that you get depends on the reason for why it's unstable, where that ratio falls. And you can see on the right there's a bit of a graph showing that depending on how many neutrons to how many protons you have and where you fall on that would dictate whether it's alpha or beta or maybe even gamma radiation. So you can actually predict the sort of radiation you're going to get based on the ratio of protons to neutrons. You can't necessarily predict when it's going to happen though. Nuclei with an atomic number greater than 83 are going to be radioactive. Now, this being said, it doesn't mean that nuclei under 83 can't be radioactive, but basically if they're above 83, it's just a given that they are radioactive. Underneath that, you're looking for specific isotopes. For example, carbon-14, that atomic number is 6, which is under 83, but carbon-14, because of that ratio between protons and neutrons, that's what makes it unstable. All right. So let's look at our three types of radioactivity. So we'll start off with alpha particles. So you can see this little symbol here. This is the alpha symbol, or the Greek letter A. Now, alpha particles are the biggest kind. They have a positive charge because they're basically the same as a helium nuclei. So there's no electrons, there's no negative charge. There is only 2 protons and 2 neutrons. And remember, neutrons don't have any charge, they're neutral, but protons have a positive charge. So combining all this together, you actually end up with 2 positive charges. So that's why overall there's a 2+ charge on it. Now, they can travel a few inches through the air, but they're pretty weak. They're kind of big and clunky, and you can really stop them just with a sheet of paper and protect yourself. Your clothing protects you from it. Okay, so what we see here is with alpha particles, when you have an atom that decays because of it, what you'll see is you'll see the number of protons here, it's 92. That's going to drop by 2 because it's going to get rid of 2 of them. So it goes from 92 down to 90. And then the number of neutrons, which is the black circle here, which is originally 146, that's also going to drop by 2 down to 144. So you end up going from 92 and 146 down to 90 and 144, and the difference there is you've lost 2 out of each of those, and that's because that's your helium nuclei being given off there. Okay, so that's alpha particles. Beta particles, a bit smaller, a bit more energy. So these guys actually happen to have a negative charge, and they're basically fast-moving electrons. And so what happens is you have a neutron, and a part of it gets flung off, and that part that gets flung off is basically an electron. And as that gets flung off, that neutron, now it's lost some negative charge out of it, is the remaining thing is positive, and so you actually get left with a proton. So what's really interesting is that beta particles are essentially electrons, very fast moving electrons, and they've got the same charge and the same mass as what we'd call a normal electron, but they've just come from a different place. They've not come from the shells, they've come sort of exploded out of this neutron and turned this neutron actually into a proton. They're a bit more energetic than your alpha particles, so they're going to get through your clothes, they're going to get through the paper. But if you have some aluminium foil or a block of wood or something like that that's a bit denser, you'll be able to stop them as well. What you see in beta decay is a bit odd, because you've got your neutron and that's going to drop down, because you basically have a neutron and it's sort of turned into 2 things. It's flung off this fast moving electron, and that's your beta particle, and that's what you can see over here in blue. But in doing that, what it left wasn't a neutron, it left a proton. So you actually end up getting 1 more proton, and that's why it goes with the protons from 90 up to 91, because that neutron got converted into a proton. But your neutrons go down because that neutron is no longer a neutron. So it's 144 down to 143 for that, and you've got your beta particle over here. Finally, gamma rays. Gamma rays don't have a charge. They're not electrically charged. They're really high energy electromagnetic waves. So like I was saying, like microwaves, not the machine, the actual radiation, or radio waves would be another example. Visible light is one form. This is all electromagnetic waves, but they have different levels of energy within them. Gamma rays have the most. And because of this, unlike the other two, they're very, very good at getting through things, and it's a lot harder to stop them from penetrating stuff. Now, in addition to that, unlike the other two, which were physical things, you had their particles, gamma rays are just energy. They have no mass, so it is a ray, not a particle. Now, emission of these rays has no impact on the atomic number or the mass of the atom. So it's not going to change the number of protons, and it's not going to change the number of neutrons. It's just energy that's given off, and often can get given off in conjunction with one of the other forms of radiation. Like I said, it's the best at getting through stuff. So if you want to protect yourself from gamma rays, you end up having to use like 1 meter thick concrete or several centimeters of thick sheets of lead and that sort of thing. So it's this is the sort of radiation that we're most concerned about being given off by nuclear reactions and that sort of thing we want to protect against. So this is what we're talking about here. You can see there's no change in the nucleus. There's still two protons and 1 neutron in there, but you've got a bit of energy being given off, and it's called a photon. It's just the name we give to that. So this is sort of a summary of what you'll see. So if it's alpha decay, you've basically lost the same thing as a helium nucleus. And so your mass number will decrease by 4 and your atomic number will go down by 2. Okay, if it's beta decay, it's given off a beta particle, that's that fast moving electron. You won't see a change in the mass number, but you'll actually see the atomic number go up by 1. If it's gamma ray or gamma emission, it's just energy, and you don't see a change in either the mass number or the atomic number. This is what I'm talking about in terms of how well they penetrate through stuff. So you can see there, pink dots are the alpha particles, and they're being stopped by paper. They're not getting any further than that. The beta particles can get through the paper, but aluminium foil is going to stop them. Also aluminium shielding. But gamma rays are the worst. They're going to get through that paper, they're going to get through that aluminium, and the only thing there we've got stopping them is lead, and quite a bit of lead. They need something really substantial to stop them and to stop them from penetrating through. All right, so here's a question for you to do. You've got 3 atoms there. You're told how many protons, neutrons, and electrons they have at the start and how many they have at the end. Now, taking what we've just gone through, see if you can work out what type of radiation each one is. So pause the video now and give that a go. Alrighty, so how did you go with that? Now, what we're going to do, we'll look at the first one. Now, we start with 6 protons and we finish with 6 protons. Okay, so we start with 7 neutrons and we finish with 7 neutrons, and the same for electrons, start with 6, finish with 6. This tells me that I've had no change across the board, and only one type of radiation had no change, and that was gamma radiation. So that's why I've got no change there. It was because it is gamma radiation. So the first one is gamma radiation. Okay, so that is the first one. The second one, if we look there, we start with 87 and we end with 85 for our protons. Our neutrons start with 124 and finish with 120, and our electrons start with 87 and finish with 87. So we've had no change there. Now, I think there's a bit of a typo here. I think that actually meant to have 122 neutrons at the end there, because otherwise this is none of our types of radiation. But if we've had 2 protons go down, that's an immediate indicator that this is alpha radiation. And alpha radiation should be 2 lost out of the protons and 2 lost out of the neutrons. So I think that's actually what it's meant to be. So this second one should be alpha. Where you would see a loss in alpha radiation of 4 is if you're talking about the mass number. So I think that's why we've got a typo here. But neutrons and mass number are not exactly the same thing. So last one, we'll just double check. We're probably thinking it's likely it's going to be beta, but we'll double check that. So we see with our protons, it goes up by 1 and our neutrons go down by 1 and electrons don't change. And that is characteristic of beta radiation. All right, so that is how you can look at a table and analyze it. So this one here, I'm just going to fix that. That should be 122 there, not 120. So yeah, that's how you can go through and you can work out the types of radiation that have occurred by looking at the start and the end of an atom. So how, though, might we actually measure nuclear decay? So we can look at the atom before and we can look at it after to see what kind of radiation it's been, but how do we see how frequently this is happening? Well, we can use something called a Geiger counter. Now, every time an atom decays, a radioactive atom decays, the detector picks this up, picks up on that radiation, and it makes a click for it. So every time something decays, there's a click. Okay, so each click indicates a single atom that's decayed. Now, it's pretty normal for it to be about 50 clicks per minute. So if that was, let's just say that's 1 click a second. So it's like click, 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 click. Maybe not quite that fast, a little bit slower than that. But that's normal. There's always some background radiation. All right, we're quite used to that. We're perfectly fine with it. But the more radiation there is, the faster those clicks are occurring because the more particles will be decaying at any one time. So at the heart of a nuclear bomb test site, you may actually see not, say, a click a second, but 50 clicks every second. And so it's going to be incredibly fast, and you might not even be able to tell that there's individual clicks. In fact, I have a little video here of someone actually showing you and how a Geiger counter works and how you can hear those clicks. And even how you can actually shield from that with like paper or a little bit of even just very thin lead or something like that. So we'll watch that now.
Today I'm going to demonstrate some radioactive materials that we see in everyday life. This is a Geiger counter, and the back side of it detects radioactivity. In each of these three sources, 1, 2, 3, the source of radioactivity is alpha particles, which is the helium nucleus emitted by the radioactive material. This is a Coleman lantern, has a lantern mantle that goes in a Coleman stove. It has some thorium in it that's radioactive. This is a smoke detector, and it has americium, also a radioactive material, to help to detect smoke. So quite a good bit of radioactivity there. This is a piece of Fiesta ware, a dinner plate with a glaze that has uranium oxide in it. These were manufactured before World War II, and in fact there was enough radioactivity in one of these plates that a woman placed a plate in a bag with some x-rays, and the plate took a picture of itself on the x-ray plates. So they're no longer manufactured. It's especially dangerous when the plate is cracked, then the uranium oxide can get into your food, and that's really not so good. This is a piece of lead that you can use to shield any of these sources. Alpha particles aren't that energetic, and all you need to shield yourself from, say this Coleman mantle is this lead. So there's no shielding, and here's with shielding, the same for the other sources. So if you want to protect yourself against various sources of radioactivity in your life, I suggest a lead suit.
Okay, so hopefully you got something out of that, because it's really interesting to see how things that are just around the house are really radioactive as well. Thankfully, I think most of those were alpha radiation, so not very good at penetrating through. As you can see, we're using something a bit thicker there to stop it, but you probably could use a sheet of paper. Now, here we're looking at the effects of radiation because we are exposed to radiation all the time. And generally speaking, we get very low levels of radiation. Radiation is measured in something called millisieverts. That's what the MSV stands for. So down the bottom there, you can see what's called the tolerable levels. And you're not going to have any symptoms. There's no detectable increased risk of cancer. And so a single chest x-ray is pretty low. If you're getting 2 millisieverts, that's about how much someone in the UK would get just by living in the UK and that sort of thing. It's pretty standard. So Some things will expose you to a little bit more, and that sort of thing. Some don't expose you to very much. If you work for an airline, because you're up in the air, you're actually exposed to a bit more what we call cosmic background radiation and that sort of thing. So airline crews tend to get a little bit higher exposure than the average person. That's about 9 millisieverts. If you're getting a CT scan, that is a higher exposure, but it's still an okay amount to get and that sort of thing. Moving into the moderate risk range, this is where you've got no immediate symptoms, but you have increased risk of serious illness later in life. And so you can see there at those different levels what can happen and that sort of thing. And once you've reached about 1,000 millisieverts, you have about 5% higher chance of cancer. Which is unfortunate, and it does happen. And sometimes we get exposed to these things for different reasons that are perfectly reasonable reasons, and that is just a chance we end up having to run the risk of. And other times it's because we're talking about something that has gone really, really wrong and we've been exposed to it. The high risk, which is our last range there, is potentially fatal radiation sickness, much higher risk of cancer later in life. Now, it's unlikely anyone is going to any of you is going to be exposed to this level of radiation. We're talking some pretty serious levels. 2,000 millisieverts is acute radiation sickness. Basically what happens is you've got that radiation is penetrating through your body and it is doing damage to the tissue and to the DNA in those tissues and basically killing it off and stopping it from functioning. You can read some of the symptoms on the right side there, but acute radiation sickness occurs at 2 millisieverts. 5,000 millisieverts is actually going to kill about half the people who are exposed to that level in a month. And if you receive 10,000 millisieverts, that's going to kill you within days. So it's unfortunate, but at least we're aware of these levels and we know also how to manage them, and we have ways of detecting them, which is always good. So moving on from that, we're actually going to talk about with radioisotopes as they decay, how we record that rate and how we measure that. So radioisotopes are unstable. They don't last and they decay, but they decay at different rates. And we don't talk about, by this point in time, it's all going to be decayed or anything like that. We actually talk about how long it takes for half of a lot or half of a sample to be decayed. So some will decay really, really quickly. They might only exist for fractions of a second, and others can take years to decay. And so we express how quickly they decay in terms of what we call a half-life. Now, I want to be very clear about this. Half-life is a period of time, and it is the time, and this is really important, is the time that it takes for half of the radioactive nuclei in a sample to decay. So it's not about half the time, it's actually about how long is it going to take for this to go from 100% to 50%, and then to 50% of that, to 50% of that. And so it's how long does it take for the amount you've got to halve, and that sort of thing. So what this might look like here, we've got a diagram. At 0 half-lives, before any time has passed, everything is what we would call the parent isotope. Everything is the radioactive substance. But after however long that half-life is, let's say it's 10 days, after 10 days, half of that sample has actually decayed. Okay, after another 10 days, what you'd expect is not all of it to decay, but half of what it was after one half-life. So if you had, let's say 20 isotopes to begin with, at one half-life you would have 10, and at 2 half-lives you would have 5. Okay, so after one half-life you've got half of your original sample. After 2 half-lives you've only got a quarter, and that's because a half of a half is a quarter. And then you go a half of a quarter, which is an eighth, and a half of an eighth, which is a 16th, and you keep on going that way down. Now, really important to understand that atoms don't just vanish into nothing. They don't disappear. But what we talk about is the radioactive one. We call that the parent, and the parent turns into the daughter. And the daughter one will be stable. And that's why it's being turned into that, is because that's how it's getting to that stable state. All right. So let's say you have 100 grams of radioactive carbon-14 or C14. How many grams would you expect to be left after one half-life? Now, you don't need to know how long a half-life is to work this out. If one half-life has gone, how much will be left from 100 grams? And then how much will be left after 2? Pause the video and see if you can work this out. All right, so we're starting with 100 grams. After one half-life, okay, we're going to have half of 100. Half of 100 is 50. So how many grams are left after one half-life? 50 grams. Okay, but if we have another half-life, so this is another one full half-life, however long that may be, we're going to have half of 50. So half of 50 is 25. So after 2 half-lives, you're going to have 25 grams. All right, so that's actually how it works. You decrease the amount by half each time. All right, so it doesn't go from 100 to 50 to nothing. It goes from 100 to 50 to 25, then to 12.5, then to 6.75, and however much it is as you half that and go down. All right, so let's try it with an actual number. So if the half-life of carbon-14 is 5,730 years, how much would it be? How much time would have passed after 1 half-life, and how much would have passed after 2 half-lives? So pause the video now and see if you can work that out. Okay, so let's go through this. If it is 1 half-life, so you're starting off with your sample here, you're going through 1 half-life. Okay, this is going to be this is going to times by 5,730. So that's how long it's going to be. It's going to be 5,730. So after 1 half-life, to whatever you have here, which is half of that sample, it's going to be 5,730 years. If you go again, it's going to be another half-life, okay, which would be another 5,730 years. Okay, so you're actually going to add those two values together. So that'd be 0, that's a 6, that's a 4, that's a 10, plus another one is 11. So it's going to be 460 years. All right, so if you know however many half-lives have occurred, you just add that many sets of the numbers together. Okay, or you can multiply it. I could have gone, it's been 2 half-lives, said 2 times 5,730. That would be the other option. Okay, and that's how you're going to work out how much time has actually passed. Now, if you know the half-life of the sample and the amount of time it's passed, you can actually calculate how much will be left. So this is sort of combining the last two things together. So for example, if I have a 10-gram sample of cobalt-60, it's got a half-life of 5.27 years. So after 10.54 years, how much will there be? Well, first of all, how many half-lives have passed? So I'm going to take how much time has passed and divide that by the length of a half-life. So 10.54 years have passed, and I'm going to divide that by the length of a half-life, which is 5.27. So that gives me 2. So what that tells me, well, 2 half-lives have passed. Okay, so if 2 half-lives have passed, and I started with 10 grams, so after 1, I would have been left with 5, and after the second one, whatever half of 5 is what I would have left. So half of 5 is 2.5. So what this means is I'm going to have 2.5 grams left. Now, we can also graph decay, and what you'll see is this sort of graph on the left here. Okay, and it decays in pretty much the same shape because that's a decay graph, and so they have a consistent shape to them, which is nice and handy. So if I had a sample of 40,000 radon atoms, and they're trapped in a basement sealed, and the half-life of radon is 8 days, how many of those atoms are actually going to be left after 32 days? Pause the video, see if you can work that out. Okay, so this is like the one on the slide before. So what we're going to do is go, well, how many half-lives have occurred? So I'm actually going to go 32 divided by 8. This is equal to 4. So therefore, 4 half-lives have passed. Okay, so what I'm going to do is I'm going to go, okay, I started with 40,000. I'm going to go to 20,000. I'm going to basically divide it into 2. That's 1 half-life. That's the first one. Then I'm going to go and divide that. So that's going to be 10,000, and that's my second half-life. Go over here. 10,000 divided by 2 is 5,000. That's my third half-life. And then up here, half of 5,000 is 2,500. That is my fourth half-life. With what that means is that is how much I have left. So it's going to be 2,500 atoms of radon will be left. Okay, so that's how you can go through that. Now, radioactivity doesn't always need to be big and scary. We actually have some ways of using it. So the first thing that we can do is we can use what's called radiometric dating. And that's where we look at rocks and fossils and we use the amount of radioactive isotopes left in them to try and work out how old they are. It's not actually about taking rocks and fossils out to dinner and a movie. That's not what we mean by dating here. What we mean is just working out how old they are. Okay. We can produce electricity using it at nuclear power plants. So that's what we've got a picture of over here. That's a nuclear power plant. And we can do nuclear fission there, and that's going to release a lot of energy, and we can get that and we can use that and turn it into electricity that we can put back into the electrical grid, which is really handy. We can also use it to treat cancer, which is really interesting because an exposure to radiation can cause cancer, but because what it's doing is killing cells, if we can target and basically use that radiation specifically on cancer cells, we can actually kill the cancer cells with it, and that's called radiotherapy. It's sort of something you might do like you would do chemotherapy or something like that. We can also use something that's called PET, or positron emission tomography. You do not need to know that name. That's just for those who are interested. That's what it stands for. But you can use it to diagnose disease and that sort of thing. You might have take a sample of a radioisotope, and then you're able to go into specific sort of like an MRI type machine, and they're able then to use that, and it's able to pick up on where that isotope is emitting the radiation from, and you can see what's going on in the body. Finally, what we can do is we can hit food with radiation and irradiate it. And what that's going to do is it's going to kill any unwanted microorganisms in the food, allowing us to preserve it for longer. So those are some really good things that we can do with radioactivity, but it is important to acknowledge that in the past we haven't always done the right thing. So I've got a video here that's looking at the misuse of radioactivity, and it's looking at the atomic bomb. And it is really good to make sure we're aware of our history. So I'm going to play that for you now.
We tell a lot of stories about science and politics on Crash Course, but it's hard to get much more political than the Manhattan Project. This is the story of the bomb that earned a capital B, and the scars it left on 20th century science and culture. It's not a happy story. Sorry in advance. The story picks up where we left off last time, with Einstein writing the president of his new homeland, the United States, urging him to build a nuclear weapon before Hitler. But how did Albert even know about this amazingly powerful weapon? For that, we turn to Hungarian-American physicist Leo Szilard. Szilard read about Ernest Rutherford's work with electrons, and in 1933 realized that it was theoretically possible to split apart an atom's juicy center and create nuclear fission, releasing vast amounts of energy and thus splitting apart another atom, and another, and another. Thus, Szilard came up with the idea of a nuclear chain reaction, which could mean a new form of energy, or a superweapon. Szilard, with the help of hotshot Italian physicist Enrico Fermi, quickly patented the idea of a nuclear reactor, or atomic pile, in 1934. This device would cause a self-sustaining nuclear reaction. Then, in 1938, German physicists actually achieved fission in the lab. And also, Hitler annexed Austria, and a year later, Poland. War descended once again onto the world. Szilard decided that only his and Fermi's invention could save it. So he drafted a letter to President Roosevelt with some input from a couple of other physicists, only Szilard wasn't famous enough to just, high-five Roosevelt and get a nuclear weapons program off the ground, but he knew someone who was. Albert Einstein, the most famous scientist in the world, and possibly ever, signed Szilard's letter. It was only 2 pages, and it's really worth Googling. It basically said, there's the possibility of this new superweapon, and the Germans might get it first. Now let's be clear, Einstein was a pacifist, but he was also like a very smart, deeply pragmatic person. In his mind, the only question was, would the Americans, Germans, or Russians split the atom first? And he foresaw a potentially very bad ending for Germany, the Jewish people, the free world, and science. He foresaw literally the end of the world. What happened next is really, really hard to understand from today's perspective. The US government, with a little help from Canada, ran an enormously expensive and secret weapons program for 4 years. Secret even from Congress. There were no leaks, so almost no one on Earth understood the possibility of nuclear physics until it was too late. This program was codenamed the Manhattan Project, and it was perhaps the first and clearest example of big science. Government-sponsored, multi-year, multi-sited, field-defining work. The Manhattan Project involved 43,000 people, including a who's who of European and North American scientists in the 40s, from Szilard and Fermi to the great Hungarian-American mathematician and computer scientist John von Neumann. The project had several parts, but most of the sciencing happened in a couple places. Take us on a fateful ride, Thought Bubble. First stop, the University of Chicago, underneath the football stadium. That's right, the biggest science ever got physically started in a place no one would ever look for it, which sounds like the plot of a B-movie. There, in December of 1942, Enrico Fermi, the architect of the nuclear age, created the very first controlled nuclear chain reaction, Chicago Pile 1. Keep in mind, the Europeans who'd fled Hitler and the Americans and Canadians who were now managing their novel experiments had no idea how far Hitler's team might have gotten. Everything was secret, new, and a guess. This was science at war. Second stop, the mines on the Navajo Nation, which included parts of Arizona, New Mexico, and Utah. Here, starting in 1944, the people who call themselves the Dene mined a yellow rock containing naturally high amounts of the heavy metal uranium. The Dene would continue to mine the nation's uranium for decades, until 1989, long after the peak of the Cold War. No one knows the full extent of the radiation exposure, but we can uncontroversially say that mining radioactive ore led to higher rates of lung cancer. The US government didn't act to address this problem until 1990, a long time after World War II. Okay, back in time, third stop, Los Alamos Laboratory in New Mexico. Here, American physics boss Julius Robert Oppenheimer, aka the father of the atomic bomb, oversaw the project's scientific research and the design of the nuclear weapons. And on July 16, 1945, the team led by Oppenheimer set off the world's first atomic explosion at the Trinity site near Los Alamos. The bomb was much bigger than anyone had anticipated. A large mushroom cloud appeared high over the desert. The test was a success. Famously, Oppenheimer summed up the moment by quoting the epic Hindu scripture, the Bhagavad Gita.
Now I am become death, the destroyer of worlds.
In the story, this is a line that Vishnu says when he takes on a fearsome, multi-armed form, which meant basically that Oppenheimer recognized two things. Developing a nuclear weapon was like being a god, and this weapon was about appearing more fearsome to one's enemies. Thanks, Thought Bubble. By mid-1945, the biggest enemy of the democratic world was no longer Germany. The Allies had invaded and retaken France in June. Now the US wanted to end the Pacific War with Japan. And the United States had a totally new weapon, one that created devastation on an unprecedented scale. The only choice left was whether or not to use it. Most historians today agree that the reason for dropping the bomb cited at the time, that is to prevent a long, drawn-out war with Japan, is wrong. Part of the challenge in writing the bomb's history, especially right after the war, was that many official documents were classified. Once documents began to be declassified, such as Truman's diaries at the Potsdam Conference, which became publicly available in 1978, historians began to change the narrative of why Truman dropped the bomb. President Truman, Roosevelt had died earlier in 1945, was aware that Japan was militarily weak, and American victory was basically inevitable. Truman was also quite aware of the number of casualties that would result from the use of an atomic bomb. The decision to drop it was a well-informed one. Besides immediate military victory, two other reasons factored into this decision. One, to justify its monumental cost, and two, to intimidate all enemies, present and future, of the United States. On August 6, 1945, the Enola Gay, a B-29 Superfortress bomber named after the mother of the pilot, took off from an island 6 hours away from Japan. At just after 8 in the morning, Hiroshima time, the Enola Gay dropped a 10,000-pound uranium-235 bomb nicknamed Little Boy that exploded over the city. This was the first and deadliest atomic bombing in history. 3 days later, on August 9, 1945, the United States dropped a second atomic weapon, a plutonium-239 weapon, nicknamed Fat Man, on another port city, Nagasaki. About 200,000 people died in the bombings and in the months afterward. Japan surrendered unconditionally. It remains the only nation to have been attacked using an atomic weapon. The long-term impact was unknown and unknowable. Even the scientists who created the bomb didn't know what would happen, although they had some pretty strong guesses. After the war, Oppenheimer became director of the Institute for Advanced Study at Princeton, and now there's an opera about him. Japan rebuilt, the United States experienced an unprecedented economic boom. Yet the end of World War II and the revelation of the Manhattan Project did not bring about world peace, but a smoldering global super conflict called the Cold War between the Soviet Union and the United States. The stakes? Control of most of the world. The rules of this game? Nuclear physics. The units of success? Number of atomic bombs, size of atomic bombs, And that's it. Yeah, weird for the conflict that pretty much organized global politics for 40 years. Okay, so what did the physicists come up with? The thermonuclear, or hydrogen bomb, which used fusion, or the joining together of nuclei, to create an even bigger reaction than the first generation fission reactors had been able to. The United States invented this one too. The Teller-Ulam design, named after physicists Edward Teller and Stanislav Ulam, is still secret to this day, which is kind of amazing. Teller was intense. He advocated for using thermonuclear weapons for all kinds of reasons, including digging out convenient giant artificial harbors, you know, a totally justifiable use of a novel superweapon. Jokes aside, the United States and the USSR continued to build and test these weapons. Between 1946 and 1958, the US tested a series of gigantic nuclear bombs at Bikini Atoll, which caused permanent damage, displacing the Bikini Islanders forever from their own nation. This is just one of the most heinous examples of the lasting social and ecological damage of nuclear physics. Nuclear fission used for energy production has not been blameless either. You might have heard of the terrible accidents at 3 Mile Island in 1979, Chernobyl in 1986, and Fukushima Daiichi in 2011. You may not have heard about the accident in 2014 at the waste isolation pilot plant in New Mexico, when the wrong brand of kitty litter was used in containment. A drum of nuclear waste exploded. Nuclear waste is incredibly dangerous for thousands of years, and there's literally tons of it, and no one knows what to do with it, so it all comes down to kitty litter. Anyway, we'll return to the Anthropocene, or the physical signs of global ecological collapse, a little later. The different applications of nuclear energy are still hotly debated today, and so are the different ways of telling the history of this technology. For example, when the Smithsonian National Air and Space Museum tried to mark the anniversary of dropping the atomic bomb on Hiroshima with an exhibit in the 1990s, a debate erupted. Was the United States justified in using this weapon? How should historians of technology think about weapons? In fact, this became known as the History Wars. On the application side, many groups of scientists, such as the Union of Concerned Scientists, have criticized nuclear weapons and energy programs as unnecessary. That is, these can be seen as good examples of the problem of creating shiny new technologies simply for technology's sake. Or maybe, as social scientist Carol Cohn pointed out in 1987, in her classic portrait of the US culture of strategizing about global nuclear war, sex, and death in the rational world of defense intellectuals, the whole point of building bigger, better weapons of mass destruction was just to prove you had the bigger bomb.
Alrighty. So, sad to know that that's part of our history, but it's always good to not forget those things so we don't make those mistakes and do those things again. But I've got some questions here for you. The answers may or may not be in the notes, but it's always good to practice our research skills. So if you're not sure of something, go and look it up. But pause the video now and answer these questions. Alrighty, welcome back. So let's go through some answers. Now it says, name 3 of the science pioneers in the study of radioactivity. Now there's quite a number of people actually who have done a lot in this area. The 3 I've got down here: Henri Becquerel, Marie Curie, and Pierre Curie. So the 3 we mentioned initially at the start of the PowerPoint. Why does a nucleus decay? Well, a nucleus decays because the ratio of protons to neutrons makes it unstable. Now, in terms of ordering emissions from least to greatest penetrability, alpha, beta, and gamma. Alpha is the worst at getting through anything, gamma is the best, and beta's right there in the middle. The greatest source of exposure to radioactivity in our everyday lives. Well, background radiation is present on Earth at all times. The majority of background radiation occurs naturally from minerals, and a small fraction of it will come from man-made elements. But naturally occurring radioactive materials are found in the ground, soil, water, all produce background radiation. Even our bodies contain some of these naturally occurring radioactive minerals. It's not necessarily always the worst thing ever. And there's also cosmic radiation from space and the sun and that sort of thing that's contributing to the background radiation around us. So there's a lot of radioactivity we're exposed to just naturally throughout the day. And that's why if you go back to that diagram, pretty much everyone would have had a background level that you'd expect to have them exposed to in a year. And it's not necessarily something we're concerned about. It's pretty normal. It doesn't seem to do us any damage at that level. It's when you get much higher than that it's a problem. Now, the last question there says, if I tell you that the half-life of felmanium 250 is 10 days, how much would be left after 30 days if I started with 1600 atoms? Okay, so 30 days divided by 10 gives us 3. So we know that there have been 3 half-lives. Okay, what that means is I'm going to go 1600. My first half-life is going to take me to 800. My second is going to take me to 400, and my third half-life is going to take me to 200. So there are going to be, after 3 half-lives, 200 atoms remaining. So that's how you can do that last one. Alrighty, this brings us to the end of this PowerPoint. Now, if there's anything you didn't understand, you can rewatch this video. You can speed it up, slow it down, jump back to anything you didn't understand and rewatch it again. And if you're still stuck or you have any other questions, don't forget to ask your teacher. They're more than happy to help you. Thank you so much for watching this video, and I'll see you in the next one. Bye.